Okay, let's start today's lecture. This speakers are also Bernard Carr and Florian Kühnel. So this is the second lecture of the primordial black holes as dark matter. So please start.
So welcome to the second day of lectures. I will be starting off, and then Florian will take over, and then I will also make some final points at the end. And I'm just starting off by giving you the plan of lectures, and you can see that in today's lecture, I'm going to first of all start off talking about the constraints on primordial black holes. Florian introduced that topic, and I'm going to talk about it in more detail. I'm then going to say something about the arguments for why we think PBHs might provide the dark matter. And then Florian is going to talk about a very specific scenario which naturally explains a lot of cosmic conundra, not just the dark matter problem. And then he'll talk about the possibility that we have some combination of primordial black holes and particle dark matter, which provides some interesting observational signatures. And then I'll make some final points. And I want to stress a point I made yesterday, which is that during the lectures, on the slides themselves, we don't make many references. And so we cite work and we show figures, but we don't always give the references. And I'll remind you that all the references, something like 500 references, can be found in the actual write-up of our Jesus lectures, on which these are basically, fairly closely based. So anyway, I want to start off by showing you a slide which Florian showed yesterday. You remember Florian was talking about the constraints which are expressed as in terms of F, the fraction of the dark matter, as a function of mass. And Florian started off actually by going back in time by showing the constraint diagram we had in our 2016 paper, and then the constraint diagram in our 2021 review. Now this is a more detailed version of the same constraints diagram, but it's based on the paper I've done with my Japanese collaborators, Kaz Kori, Yuichi Senduda, and Junichi Yokoyama. This paper just came out last year, and it is supposed to be the most comprehensive set of constraints which are currently available up to the end of 2021. It's really very hard to keep up with the literature, and we consciously said we're not going to cite any papers which came out after 2021, because the point is these constraint diagrams are changing all the time as we get more data. Now, I'll remind you the point of this diagram is that any colored shaded region is excluded. Obviously, if you want the dark matter to be in primordial black holes, you need F to be 1. And I should say this is all assuming the primordial black holes have a monochromatic mass function. That's to say that we're assuming they have a mass m with a mass width of say, delta m twiddles m. And that's an important constraint, but it's the constraint which used to be made until a few years ago. Now, obviously, this is a very complicated diagram, and it's full of acronyms, and the acronyms I'm going to explain in a moment. But at the moment, I'm not going to explain what these acronyms are. I just want to, they're color coded because different types of acronyms have got different colors. But for the time being, I just want you to appreciate the huge number of constraints there are. And all these constraints have caveats, which again I'll talk about a little bit later. But the point is, the mass range associated with these constraints, it goes all the way, if you're talking in grams, it goes from 10 to the 15 grams to 10 to the 55 grams, that's the mass of the universe. Or if you want to think in solar masses, it goes from something like 10 to the minus 18 solar masses to something like 10 to the 25 solar masses. 10 to the 22 solar masses. So it's a huge range of constraints. And the point was that, up until a few years ago, people mainly focused on constraints because there wasn't so much positive evidence for primordial black holes. The situation has now changed, as we explained in our first lectures. And but so I think I can claim that this paper is probably the most comprehensive survey of constraints. There are lots and lots of papers. Almost every paper now on primordial black holes will include a paper which include a figure which looks rather like this. But I think we can claim that at least up to the end of 2021, this was the most comprehensive set of constraints. But of course, there's far too much information to absorb in that diagram unless you stare at it for an hour. So what I'm now going to do, I'm going to break down those constraints and explain them in a little bit more detail. First of all, they're the lensing constraints. So for example, they're purple. So all the constraints shown here are the purple ones in this diagram here. But I'm just spelling them out in more detail, and I'm also explaining what the acronyms are. Well, you can read this, but I'm just going to briefly say what they are. GRB stands for gamma ray bursts. This is the femtolensing of gamma ray bursts. The point is, if you have a primordial black hole or any dark object in this mass range, it would actually produce microlensing of the gamma ray bursts. But it's called femtolensing because the scale of the image separation is more like 10 to the minus 9. It's not, microlensing is 10 to the minus 3 arc seconds, and this is 10 to the minus 12 or whatever it is. But what you notice is that this is shown as a dotted line, and the reason it's shown as a dotted line is because subsequent papers have argued that actually this effect isn't valid. All of these constraints, there are many discussions, they're sometimes controversial, and there are sometimes observational developments, which means they're no longer valid. So if this is a dotted line, it means that we probably don't believe it anymore. But on the other hand, other people might still think they are. So there's always some element of controversy in that. But the point I want to stress is that this is a tiny mass range, 10 to the minus 16 to 10 to the minus 14 solar masses, which is the mass of an asteroid. So it's fairly amazing that you have such a constraint if it were correct. Now, then we've got, going up in mass here, HSC is the Sabaro telescope, and this is microlensing observations of M31, the stars at M31, and again, this is this line HSC, and you can see the reason it's dotted is because actually the mass ranges was changed in subsequent papers. This was a Japanese group. There is such a constraint, but I mean it's been argued that the original constraint, which is shown by the dotted line, was too large, and this solid line is the one which is now accepted. So it's a slightly narrower mass range, which goes from something like 10 to the minus 10 to 10 to the minus 5 solar masses. By the way, I should perhaps just explain what we mean by microlensing. If you have a dark object going in front of a star, or normally a star, but it might be another astronomical source, the effects of the lensing is sometimes to produce double. If it's macrolensing, you produce two images, which you can see separated. But if it's microlensing, you don't see the two images, they're too close together, but you see a luminosity variation as the dark object goes in front of the object. But so it's just a question of which sources, which stars you're looking at, and in this case we're looking at stars in the Andromeda galaxy. Now Kepler, that was looking for the microlensing of stars in our own galaxy, and there you can see that it's that solid line because everyone accepts this, and this is 10 to the minus 9 to 10 to the minus 3 solar masses. Ogle, this was the Polish collaboration, and for many years they've been looking for the microlensing of stars in the galactic bulge. So you're pointing the telescope and towards the center of the galaxy. And again, the mass range here is 10 to the minus 3 to 10 to the minus 1 solar masses. So this is the Ogle line there, you can see. Now, Eros, this was one of the original microlensing searches in the 1990s, that they were looking at the in the stars in the Large Magellanic Cloud, and they got strong constraints in the range 10 to the minus 7 to 10 to 15 solar masses. So there's the Ogle line there. So you can see that. Sorry, this is the Eros line here. Okay, that's the solid line there. Now, Macho was the parallel project going on with the Americans, and that was looking at stars in the mass range. Well, the point about Macho, I'm going to come back to this. Sorry, there's a typo there. That shouldn't be times. That should be 0.1230 solar masses. So this is the there is the Macho, that little curve there. I hope you can see the cursor moving. And that was and I'm going to say a little bit more about that later, because they at one stage claimed positive evidence. Another type of microlensing event involves looking for the supernova, and the microlensing of supernova. And as I said before, I'm not giving I'm not citing any references here, which I suppose I should be, but otherwise there'll be hundreds of references, and I don't want it would be too cluttered. But the full reference can be found in the written version of these lectures. And that's a very interesting constraint, because it goes from 10 to the minus 2 to 10 to the 4th solar masses. So that's the supernova constraint there. You can see it marked SNE, quite a wide mass range. And then finally, there is the radio sources. And in the case of radio sources, it's millilensing of compact radio sources. So this means that it's milliarc seconds rather than microarc seconds is the image separation. And that's the wide range. It's 10 to the 5th to 10 to the 8th solar masses. Now, so I'm identifying these constraints, but obviously if you want to read the full details and then sometimes the controversies and get the full references, you should look at the Japanese paper. Now, then there are the dynamical limits, and again I will just go through these quickly. First of all, it was claimed that you would get constraints because neutron stars and white dwarfs, they would capture primordial black holes. The primordial black holes would go to the center, and then the primordial black holes would swallow the neutron stars and the white dwarfs. And this would therefore do two things. It would actually cause the neutron stars to disappear. So you might expect a deficit of neutron stars, but also it would mean you would end up with black holes which were, because the black holes would accrete the neutron star, and so you would end up with a black hole which could be less than a solar mass. So the initial primordial black hole would be much less than a solar mass, but by the time it had swallowed the neutron star or the white dwarf, it would be close to a solar mass. Now, those constraints were historically interesting, but actually, for various reasons, that they've now been questioned. There's also a constraint associated with supernova, because it turns out that when a primordial black hole goes through a white dwarf, it can actually trigger a supernova. There are various mechanisms for supernova, but this will be another one. So these are dotted because these are not so secure now. So these dotted lines, for example, aren't shown in the master diagram I started with. And that goes from 10 to the minus 15 to 10 to the minus 8 solar masses. So again, a very low mass range, sort of supernova mass range. Sorry, asteroidal mass range up to lunar mass range. And then there's the supernova one, which I've already mentioned as a dotted line. That's when the primordial black hole goes through the white dwarf and triggers an explosion. And that's 10 to the minus 15 to 10 to the minus 13 solar masses. So that's the supernova line there. Now, going to larger mass ranges, you see there's a big gap now. But when we go up to the mass range of, say, 100 to 10 to the 7th solar masses, I should point out that most of these dynamical effects come in at high masses, bigger than about 100 solar masses, whereas the microlensing limits tended to be in the intermediate mass range. Well, these objects, if they are in the halo, they will actually they're going to have wide binaries. Basically binaries which are of wide separation and therefore rather loosely gravitationally bound, and it's very easy for primordial black holes, if they come sufficiently close to the binary, to simply disrupt the binary through they tidally pull the two components away. And so the fact that we see wide binaries puts constraints on primordial black holes, and the constraints lie between about 100 to 10 to the 7th solar masses. And this is a solid line because, I mean, there are arguments about precisely how strong the argument is, but there's no doubt that this is a limit in principle which applies, and that's the solid line there. So it's I think that's clear. Another possibility is that if you've got globular clusters, and these are assuming the primordial black holes are in the halo of our galaxy, we're assuming the dark matter is primordial black holes, well, at least some fraction of the dark matter, Fm, is primordial black holes. You notice most of these constraints are well below F equals 1. So one isn't just saying these aren't the dark matter, we're putting very strong constraints on them, as you can see from this diagram. Anyway, the globular cluster effect, the disruption of the globular clusters, means that, you know, the fact that globular clusters exist with a certain lifetime puts a constraint, and that's a constraint which goes from 10 to the 4th to 10 to the 10th solar masses. So there's that constraint there. A related effect is if you have a star cluster in the center of a dwarf galaxy, that cluster will also get disrupted. Of course, globular clusters are existing around the galaxy, but this is in the center of a galaxy. And there's a famous case of Eridanus 2, and it puts constraints in the mass range 100 to 10 to the 6. And that's that line there. I'm not going to try and explain the precise form of the constraint. You know, it goes down and then it has a minimum and goes up again. All that's explained in the paper with the Japanese. Another important effect, which was actually one of the first effects discussed, this I think was by Lacey and Ostreicher, and this is if the galactic halo is supermassive primordial black holes, or indeed supermassive black holes, even if they weren't primordial. But you remember they really have to be primordial if they're going to have explain the dark matter because of the Big Bang nucleosynthesis constraint, you recall. Anyway, this puts a constraint between 10 to the 6th and 10 to the 12th solar masses. So this is this line here, the globular cluster line. So it's going up to very large mass ranges. And actually, this was originally claimed as positive evidence. When Ostreicher and Lacey wrote their paper, they claimed there was positive evidence for this because you needed to explain the heating of the disk. Another effect is dynamical friction of the halo. If you've got black holes in the halo, the dynamical friction of the ordinary galaxy, the visible galaxy, is going to tend to make them fall into the center, drift into the center of the galaxy. And if there are lots of black holes, they may merge and eventually form one big black hole. And that puts a constraint. This is quite a complicated constraint, but it goes from 10 to the 4th to 10 to the 12th solar masses. Now, at an even bigger mass scale, you could say, well, are there giant black holes? I mean, even, you know, masses of galaxies in clusters of galaxies. You remember the first evidence for dark matter came from studying clusters of galaxies. This was the famous Zwicky argument in the 1930s. And actually, if there were giant black holes, you would actually disrupt the galaxy or produce unexplained tidal distortions in the galaxy. And that gives a constraint on the huge range 10 to the 10th to 10 to the 14 solar masses, which is on the right here. And finally, if you imagined you had really huge black holes in the mass range above 10 to the 18 solar masses, I mean, you might say, well, I mean, that's absurd. You'll never have black holes that big. But I'll remind you that there is evidence for black holes of 10 to the 11th solar masses already in galactic nuclei. And myself and Florian and Vestinelli have argued that there could be what we call slabs, stupendously large black holes in this mass range. But there are some constraints, and the constraints come from the peculiar velocity induced by these giant black holes in our own galaxy. If there was a population of these really large black holes, then the nearest one will produce a peculiar dipole effect. A Coulomb effect would produce a peculiar velocity. And we have constraints on the peculiar velocity of our galaxy from the CMB dipole. And that basically is the constraint shown in this diagram. On the other hand, there is another constraint, it's called the Incredulity Limit, which says we're only interested in a scenario where there is at least one primordial black hole in our universe, in our visible horizon, and that's what I can't actually see the diagram. Let me just move this here. So that's the Incredulity Limit, and so they merge at 10 to the 21 solar masses. And actually, when I was referring to slabs as stupendously large black holes. That's because there is this mass range here where there are no dynamical limits excluding it. So when we were invoking slabs, we were specifically invoking this upper limit, which is something like 10 to the 18 solar masses. So a slab is somewhere between, between 10 to the 14, say, and 10 to the 18 solar masses, where there are no constraints excluding it.
Hello?
Yes.
Hello? I have
Hello.
a very naive question. In this constraint, most constraint has this the shape, triangular shape, right?
Yeah.
Inverted triangular shape, but some constraints such as wide binaries and globular clusters, you have a horizontal
Yes.
bound. So what's the difference between
Let
these?
me, I will explain what you're quite right. Most of these constraints have got a stroke, the upper limit, it goes up. And actually, this is a line that goes like M, F goes like M. And the origin of that constraint is very simple, actually. It's associated with the incredulity limit. Now, the incredulity limit, this shown here, is the requirement that you must have at least one black hole within the cosmological horizon, within the particle horizon. We call it. This is a phrase I introduced with Mary Stackley-Aradu way back in the 90s in some paper, because the idea is that if you've got less than one black hole in our horizon, it's not a very interesting scenario. And so that's what the lower limit corresponds to. And in some sense, it's trivial, but it's a constraint that goes like M. Now, there's an incredulity limit in any context. So, for example, if you're considering black holes in the halo of our galaxy, if you're assuming that these black holes provide the dark matter in halos, or at least contribute to the dark matter in halo, you can also ask, well, we must have at least one of these objects in the halo, because otherwise the scenario is uninteresting. So, for example, if I'm talking about our own halo, this is the line here. You notice all of these lines here in the halo have the same M, F goes like M line, and it just corresponds to having one black hole in the halo. And you can trivially see where the limit comes from, because the fraction has to correspond to the mass of the black hole over the mass of the halo. And therefore, that's what this line corresponds to. And you have a similar constraint when you look at clusters of galaxies. That's the line there, for example. Now, but some of these constraints don't depend on that. It's just because the wide binary constraint that the limit cuts off before you get to the halo limit for various reasons. Some of these constraints, there are other limitations on the constraint. But I mean, for where you don't have another limit, this is where the limit always cuts off. So thank you for raising that point. I don't normally explain that. Great. Okay, so now let's carry on. I'm going to move this figure to the side. That's right. So now the next figure, the accretion constraints. Well, again, I've combined in one diagram here the accretion and the LIGO events, the LIGO Virgo limits. And again, I'll just briefly say what these are. There are LIGO, the O2 refers to the original run, O1 and O2, they're now up to O4 of the LIGO Virgo runs. And there are various constraints here, some associated with background limits, the background gravitational waves, but some are associated with the actual number of the events themselves. I've already mentioned the possibility that, we may be in principle detecting primordial black holes with these LIGO Virgo events. But even if you don't believe that, you have a constraint on the number of primordial black holes. And these are the constraints. Now, the constraints are quite complicated because it depends on when the binaries form and things like that, and details of the surveys. But all of these constraints have got various, I could talk about each of them for an hour, essentially. But these are the LIGO Virgo constraints. So there's the O2 and there's O1. And you see they go from 10 to the -1 to basically 100 solar masses. Now, there are also constraints, various constraints that come from accretion effects. because you know, if you've got black holes, they will accrete, especially if they're in binaries. Of course, the accretion models themselves have got various uncertainties, but these are constraints associated with the X-ray and radio sources. In fact, I think the background sources. So, but these are the lines here, a little bit cluttered here, but you can see here the X-ray. These are in blue, and the radio, and they go from something like 1 to 1,000 solar masses. But the actual X-ray binaries, they're the ones, you know, the first X-ray sources like Cygnus X1 were black holes detected in binaries. Well, there are lots of X-ray binaries. We don't know whether they're primordial black holes, of course, but we get constraints. And these constraints, this is the solid line. A lot of these lines are broken because there are uncertainties in the observations, but this is a solid line, the X-ray binaries. Again, if you want the references, you must look to the printed paper. And this is a huge range from something like 10 to 10 to the 7th solar masses. And then there are constraints that come from accretion. Now, these are actually, this is the accretion of the black holes generates radiation, which is going to affect the background radiation. The spectrum and the anisotropy is in the background radiation, and these are detected by the Planck satellite. So Planck here refers to the Planck satellite. But it all depends on whether you've got disk accretion or spherical accretion. Again, this topic has a long, long history. It goes back originally to some paper by Ostreicher et al. But there are many papers on this. But basically, the most up-to-date constraints are shown in here by yellow. And then finally, the edges observations, which some of you will have heard about. It's even claimed that some of the edge observations might be evidence for primordial black holes, but at least we get constraints, and those constraints are shown by this yellow line here. So again, so I've now discussed the constraints in more detail. The evaporation constraints, well, obviously, the black holes which are evaporated, which are the ones below roughly 10 to the 15 grams, or more precisely something like 5 times 10 to the 14 grams. They can't provide the dark matter because they're no longer here. But it's still interesting to actually put the constraints in terms of the fraction Fm. Now, of course, Fm is defined as the fraction of the dark matter in the black holes. These black holes have evaporated. And so they, in principle, F is now 0. But I can calculate what would F have been if they hadn't evaporated, and that's essentially what we mean by that. If the fraction of the dark matter, if they hadn't evaporated, is given by this, and the various constraints come from Big Bang nucleosynthesis. I've again, remember, these are black holes which are evaporating. They produce particles, and these particles would mess up the standard Big Bang nucleosynthesis picture unless you had a constraint. And you can see these constraints are interesting. You know, they're down at the 10 to the -5 level. And for the Big Bang, they go from 10 to the 10th. I'm putting this in grams. I mean, I've got it solar masses at the top, but in grams, it's from something like 10 to the 10th to 10 to the 13 grams. Other constraints, the CMB anisotropies, this is rather technical, and it's a surprisingly strong constraint, which is that if you are generating a lot of heat from these evaporations, it will reduce anisotropies and thermal distortions in the microwave background, and this is what this constraint is here. That goes from 10 to the 30 gram. Sorry, I made a mistake. 10 to the 30 should be 10 to the 13 to 10 to the 17 grams. The most famous constraint is the extragalactic gamma rays. I referred to this in my first lecture. The idea here is that the black holes which are evaporating today, they will have a temperature of 100 MeV. They'll produce a gamma ray background at 100 MeV. So measurements of the gamma ray background tell you what fraction of the dark matter can be in black holes of that particular mass. So this is a limit down here at the bottom of the pink region. And I referred to that in my first lecture. You know, this was the rather bad news in 1975. But you can extend the constraints to much smaller black holes, which are these are the ones which evaporated earlier, but they're still producing a gamma ray background, but more in the X-ray band, because it's a lower energy because of the redshift effect. And you can also extend it to black holes somewhat bigger than 10 to the 15 grams, because although they haven't completely evaporated, they partially evaporated, and again producing a gamma ray background at somewhat lower energies. And that's why you have this pink, the extragalactic gamma ray line looks like this. There's a gap at 10 to the 15 grams. I won't go into it. So there's a jump. But so you see, this is the strong constraint, and it goes down to 10 to the minus 10. And that applies between 10 to the 14 and 10 to the 17 grams. This is historically the earliest constraint we had. That goes back originally to 1976, but has been obviously strengthened. And then another constraint is associated with the electron and positron cosmic rays. The evaporating black holes in this mass range also produce electrons and positrons, and there would therefore be a contribution to the cosmic rays, which might be from primordial black holes. You could even argue some of them come from primordial black holes, but the point is that you have a constraint between 10 to the 14 and 10 to the 17 grams, which is this constraint here. Now, so but of course, if you want the dark matter, you're actually only interested in the regions on the right here. But I mentioned this because a huge amount of effort has gone into considering the evaporation constraints, even if they can't make the dark matter, because they're of interest in their own right. And so I'm doing this in slightly more detail because this is a rather I've just taken the basic effects, but you can ask in more detail, well, what are all the various other constraints on evaporating black holes? Because I've only mentioned some of them in this diagram here. And here I've expressed the fraction. I've not expressed the limits in terms of the fraction of the dark matter. I've expressed it in terms of the fraction of the universe collapsing. And this, remember, there's a simple relationship between beta and m. Basically, beta is very small compared to F. You remember I gave the argument last time why, even if primordial black holes have a high contribution to the dark matter today, it corresponds to a very small collapse fraction. And the ratio between them just has an extra factor which goes like m to the half. And so this is the far more detailed discussion in the paper with the Japanese. Again, it's all expressed in terms of, as a function of mass, but now it's giving a constraint on beta rather than FM, which makes more sense because technically these black holes don't exist anymore. So in some sense, beta is more physically sensible. But you can see that these constraints break. For example, the Big Bang nucleosynthesis constraint breaks up into lots of sub-constraints associated with effects of nucleosynthesis. The CMB constraint breaks up into the spectral distortion constraints and the anisotropy constraints. And all these, the extragalactic cosmic rays, there's also the antiprotons in cosmic rays and antiproton background. And there are lots and lots of constraints in the range above 10 to the 15 grams, which I haven't gone into. But these are much more relevant to the dark matter problem because in principle, remember, if F is 1, in principle, there is a mass range, above, say, 10 to this line, the dotted line corresponds to F equals 1. And so there is a mass range above about 10 to the 17 grams, where in principle, primordial black holes, even though they're partially evaporated, could provide the dark matter. Again, this is a very complicated diagram, because people have been working on these constraints for years and years. But I just want to compare this constraint with the one which we had in 1994. You remember this? I showed this in my first lecture. These were the constraints basically corresponding to this diagram, the relic, the entropy, and the nucleosynthesis constraints and the gamma ray constraints. So basically, this diagram you can see is rather similar to this diagram. But if you look at it in more detail, you've got this figure for the evaporating black holes. So this left-hand region here corresponds. And of course, it's more complicated because it reflects the huge amount of work which has gone into this topic. Because remember, up till a few years ago, most of the emphasis was on constraints. And so this is the, again, this figure is in the paper with the Japanese. Now, so finally, in terms of constraints, let us put together all these constraints, both the evaporating and the non-evaporating constraints, on beta m. This is on beta now. And this is all put together now in this master diagram where, again, it's color-coded as before, and by now you probably know what all the acronyms correspond to: large-scale structure, dynamical friction, X-ray binary, cosmic microwave background, gravitational waves, gravitational lensing, and Big Bang nucleosynthesis, entropy, in Planck-mass relics. But the point is that, again, everything above the line is actually excluded. And so what you see from this diagram is that the fraction of the universe collapsing is tiny. Look at this, all the way down to 10 to the minus 30. So over the whole range, 10 to the minus 5 to 10 to the 55 grams, I mean, well, it only goes up to 1, of course, when you go above 10 to the well, we want f to be 1, so this is beta, so you can't really, but beta, f equals 1 is a line which slopes there, but you have to, of course, to be above 10 to the 15 grams if you're going to make the dark matter. So really this summarizes a huge amount of work. I mean, the subject of primordial black holes is now 50 years old, and basically this diagram summarizes the constraints of hundreds of papers over 50 years. But the point is, the bottom line is, they're really important constraints on beta. And those constraints on beta, the collapse fraction, are in turn given constraints on the cosmological models. And that was the justification for actually studying primordial black holes. They're a vital probe of the early universe. But of course, a skeptic might say, well, since beta is so small, observationally, why shouldn't beta just be 0? Why should there not? And as Florian explained in his lecture yesterday, generally speaking, the collapse fraction is expected to be small. Now, but once you've got that, you can get constraints on the power spectrum. Now, you remember that Florian showed this picture in his lecture yesterday. This was in 94, this was the original constraints on beta. And these were the constraints you got on epsilon, which was the amplitude of the horizon scale fluctuations. And you remember that you go straight from beta to epsilon, and if they form from Gaussian fluctuations, and that was one of the interesting aspects of primordial black holes. They put strong constraints on the collapse fraction. Nowadays, I can do the modern version of that using, this was the master diagram from the Japanese paper, and that's the constraints on the power spectrum. Remember, the power spectrum is related to epsilon. Epsilon is the horizon amplitude, and the power spectrum is essentially the square of that. But it's essentially the same diagram, and again, it's color coded. So again, this is showing how you get constraints on the power spectrum from studying primordial black holes from all these limits. And so that's again very interesting. Of course, we have constraints on the power spectrum from later observations of a larger scale observations of CMB and galaxy clustering, but this is unique to primordial black holes. Now, you might say, well, why am I spending so much time? And I have actually spent a lot of time talking about these constraints. I want to point out that these constraints are not just nails in the primordial black hole coffin. So the point of these colored diagrams isn't just to say primordial black holes exist, because the point, and why do I say that? Well, first of all the constraints have caveats, and they may change, and they have changed. Florian introduced this in his lecture. He pointed out how some of the constraints we had in 2016 have either gone away or changed. The same is true today. So that diagram which I showed you from the Japanese paper, that will change every year. as the change, it'll change because we get new constraints. Some of the old constraints will go away or get weakened as a result of observational developments. So all the constraints have caveats. And in particular, all those constraints I've shown so far assume you've got a monochromatic mass function. The other point is that the constraints are normally f is much less than 1. I mean, it's only f equals 1 if you're interested in dark matter, but constraints are interesting even if f is much less than 1. The black holes that exist in galactic nuclei, they've only got something like 10 to the minus 5 of the dark matter, but they're the ones, you know, which are so interesting. Many people devote their lives to studying supermassive black holes. It could be argued that the most interesting component of the universe are human beings. But of course, our contribution to FPBH is completely tiny. Whatever it is, 1 in 10 to the 12th or something. So, you know, we shouldn't be too obsessed with the dark matter. Although we're talking about primordial black holes as the dark matter, they're all dark, and they're interesting even if F is low. But maybe the most important point is that these constraints are interesting. I mean, each constraint is a potential signature. Even if F is low, it's a potential signature. And historically, many of these constraints arose out of claims that there was originally a positive signature. So I refer to the disk heating, for example. Originally, Ostreicher and Lacey argued this was evidence that the dark matter in the halo was million solar mass primordial black holes. Well, we no longer believe that because we have other reasons for why the disk may get puffed up. But nevertheless, each of these constraints could become a potential signature. And maybe, and then in fact, that's going to be the theme of Florian's lecture, which follows mine. But the other point is that actually we've assumed that we've got a monochromatic mass function, which means in practice that the width of the mass width is only delta m of order m. And I'm now going to explain that this is not true. By the way, I'm taking more time than I expected on this lecture, so I'm sorry about that. But will we be able to go on till 9:30? Sorry, 9:30 my time.
40 minutes.
If not, I'm going to cut off my lecture at this point. But how long? What is the actual? Of course, we didn't start till 9:15. How long is the total? Oh no, we've got 2 hours. We're fine, haven't we? I take it back because I was forgetting. But I still have an hour, so I've still got another 15 minutes. That's fine. So Florian, there's no problem.
And I think you started 10 minutes. I think you started 10 minutes late. I think you now have 20 minutes, Bernard. Or
exactly. So I've still got another 15 minutes. That's fine.
Yeah, at least probably 20 or 25.
Okay. So anyway, so those are the I want you to bear in mind those constraints. So although I spent a lot of time discussing the constraints, I don't want you to remember there may be ways of getting around the constraints. And so I think these comments are very important. But now I do want to actually go into a little bit more detail about some of these points. Because now let's get on to the question of, can the primordial black holes provide the dark matter? But in other words, can F be 1? And you know immediately from this diagram, you can see from the diagram here, for example, on the left, F is 1 corresponds to this dotted line here. And so your first impression from looking at this diagram, now remember that there are lots of dotted lines here, but your first impression is that actually F can't be 1. So you might think, well, there is a little range up here, you know, where there are no constraints. This is in the slab range, stupendously large, but of course no one believes that the slabs could be all of the dark matter because they're too big to fit in galaxies. So at first you might argue that there really aren't any constraints. So bear in mind that there really aren't any regions where you can have F equals 1, but bear in mind that this F, these dotted lines don't count. So there are a few ranges. But actually what we're going to argue is that there is a range around F equals 1, where F could be 1 around 1 solar mass, despite the fact there's lots of colored regions there. So that's what I want to focus on now. So, well, first of all, let me put this in a historical context by referring back to the problem of microlensing. The first microlensing experiments were looking for dark matter in the halo of a galaxy by looking at the large and small Magellanic Clouds. So those were the so-called Eros and Macho experiments. So there is LMC and SMC. They were looking in this line of sight. And as I said, the idea was that a black hole in the halo of our galaxy would get in the way of one of the stars and cause the luminosity to vary. Now, they found positive effects. In fact, the Macho experiment, they were looking for machos, but it's called the Macho experiment. Remember, Macho's massive compact halo object. They actually found a population of objects with about half a solar mass, which were producing microlensing, which couldn't be explained by normal stars. Because, of course, there are stars in the halo of our galaxy, which would also produce microlensing. This was tremendously exciting. This was about 95. So for people like me who were working in the subject, we thought this is really exciting because actually machos in that mass range could be primordial black holes that formed at the QCD phase transition. Remember, that's about 10 to the minus 5 seconds when the horizon mass is about a solar mass. Now, these couldn't be white dwarfs, for example, because they would be detected. So we were really excited. We thought, haha, primordial black holes exist. I haven't wasted my life, which by then I'd spent about 20 years on the subject. And furthermore, it had been pointed out by people that you would expect primordial black holes perhaps to form at the QCD phase transition because of the pressure reduction. In fact, at that stage, they thought it might be a first order phase transition, which made the pressure reduction even less than we think it is now. We think there is a pressure reduction now, but it's only about 30% in terms of the sound speed, but then it was thought it could be even less. And so it was predicted by various people like Dynamic that you could have a peak at a half a solar mass. So this was great. We had a scenario for making them, and Macho seemed to have detected them. However, later on, when they had more events, they found that only 20% of the dark matter could be in these objects. And so that seemed to say that the dark matter couldn't be PBHs after all. However, there was still and still is, they had something like 12 events. There is still a puzzle as to where these objects come from, because the point was that there should be, the ordinary stars produce microlensing, but there aren't enough ordinary stars to produce this amount of microlensing. On the other hand, the Eros experiment, which was the French experiment, they looked at the LMC and they had got constraints. They didn't get the same number of detections, but they had I won't go into the technical details. They had constraints. So in this diagram here, this is F against mass. This is in green is the Macho detection with the positive detection there. Obviously, all these constraints have some confidence limits, and I haven't gone into that, but they're normally 95% confidence limits. But here you can see in blue is the Eros constraints, and the Ogler constraints are shown towards the galactic bulge, are shown in purple. And so, but the point is, remember, you want F equal 1, you apparently can't have F equals 1, but it is still a puzzle that you've got a positive detection with F equals 0.2. Now, the reason I'm stressing this is because actually what we're going to argue, and Florian is going to argue in his lecture, is that actually we now think that this is the best mass range for the dark matter. But the only difference is you have to bear in mind is that we can no longer assume that you've got a monochromatic mass function. This diagram here assumes it's a monochromatic mass function. It's a limit on F for black holes of a given mass. If you have an extended mass function, which we're going to argue is the case, then these constraints have to be kept more carefully, but have to be considered more carefully. But there was other constraints that came at roughly the same time. Sorry, not constraints, I would say potential detections. And this came from searching for, looking at quasars and looking at the microlensing of quasars. And this is associated with the work of Michael Hawkins, who's one of our collaborators. He wrote a popular book on this subject, Hunting Down the Universe. But basically, remember that Matthew and Eros experiments were looking at the microlensing of stars. Michael had been looking at the microlensing of galaxies, of quasars, and he was claiming there was evidence for microlensing of quasars, but remember they're at a cosmological distance, so it's a very different time scale. It's years, decades, rather than time scales of hours, days, and weeks. And so these were some sample light curves, for example, where you see these oscillations. And the idea is that they're not actually, these are not intrinsic to the quasar. I mean, quasars vary, but the idea is that these are actually due to the luminosity variations induced by a primordial black hole between you and the quasar. And the evidence for this was rather like the same evidence for microlensing of stars in the Magellanic Cloud. You've got the symmetry in time. It's achromatic. It doesn't depend upon the color. And he argued at the time that, well, he now argues the time scale of the variation implies the mass of the microlensing body is about 1/10 of a solar mass, which is a little bit less than we're seeing for the microlensing of stars in the LMC. But he's now updated this. He's now got much more data. Obviously, this is 30 years ago. And now he gets a mass of 1 solar mass. Now, I have to say, historically, I think people were a bit skeptical of these results because, because what he was arguing is that this could be explained by if the dark matter was in a population of roughly solar mass black holes. And at this time in '93, people weren't very enthused about that. But now it's becoming much more vogue, and he's continued to push this idea. And he indeed is one of our collaborators. But it's interesting that this evidence is coming at roughly the same time from both quasar microlensing and the microlensing of stars. But there's one problem with all of these arguments, is that I've already mentioned constraints which seem to exclude primordial black holes in this mass range having F equals 1. So you've somehow got to get round. There were constraints that came from the, all those constraints from the microlensing searches, Ogle and of course Eros and Matthew themselves, but also there was a constraint that came from the lensing of supernovae, which seemed to exclude it. How do you get round those constraints? Well, the arguments that the best way is, and I think a rather convincing argument. Remember, first of all, you expect to have an extended mass function, so that's the first point. And I mentioned in inflation, you tend to have a log normal mass function. But this also has another important implication. You expect to get clusters of primordial black holes. You don't expect the primordial black holes to have a uniform distribution in the halo. They're going to be clumped. And this is represented in this diagram here, which comes from a paper by Juan Garcia Bellido, one of our collaborators and his colleagues. This is the diagram, which is this is actually this is showing the inflaton potential, but what it's saying is that your primordial black holes tend to be clumped. You've got a mass distribution here, and they tend to be clumped. Well, actually, independent of how the black holes form, even if they form in some other scenario, they are going to be clumped. And this is because if you form a population of primordial black holes, there will be Poisson fluctuations, and the Poisson fluctuations themselves will cause clumps. And now, if you've got clusters of black holes, it changes all the microlensing limits. And there are various reasons for this, but one reason is quite simply, if you imagine your dark matter, instead of being uniformly distributed, is in clumps, then there's quite a high probability that a line of sight to a star will not be microlensed. And so that's one effect. But there are various other indirect effects, which I'm not going to go into. It would be a bit too much of a detour. But the fact is, this is represented in this second diagram here. The fact is that cluster is expected. It's expected in some of these inflationary scenarios, but it's expected anyway because of the Poisson fluctuations. And this, to me, is the main way of getting around of those various constraints, excluding the dark matter being in roughly 1 solar mass primordial black holes. Well, is there any evidence for this clumping? And actually, rather remarkably, evidence has just come up in the last year from Meneghetti et al. This is one of the few slides where we've actually credited the person, because we've actually taken the slide. So this is basically this comes from simulations, and this is numerical simulations, and where you compare to the observations, and the claim is there is more clumping. There is evidence for this clumping, and so in this, let me just remove this pictures. So this is basically the simulations. So this is the galactic strong lensing. I hope I've got that right, the acronym. Florian's is saying if I'm wrong. This is the strong lensing as a function of redshift, because we're looking back to higher redshift. These are the simulations shown in gold. And here we've got the actual observations, which are shown in blue. And the point is this, that there's more of this than will be expected in the standard, these are simulations in the context of the standard model. And so there's more clumping of dark matter than will be expected, but this is precisely what is predicted if the primordial black holes were providing the dark matter, because of the reasons I've just given. So I think this is rather this clustering really is going to be crucial, and I think that Florian will emphasize that in his lectures. But the other final point is the question of an extended mass function. As I said, normally one assumes you've got a monochromatic mass function. All those constraints assume a monochromatic mass function, but actually it's most likely to be an extended mass function. And indeed, the first paper I did with Florian and Merit Sandstad, I think we were probably the first people to study this problem in detail, but subsequently many other people have looked at this. But if you've got an extended mass function, well, you have to define a function psi m, which is basically the fraction of the dark matter in a mass range around m, and so you have to integrate that to get the total PBH dark matter. And so what is the form for this mass function? There are various scenarios. This, for example, is the log normal mass function. You can have a power law mass function if, for example, with cosmic strings, you get a power law mass function where you've got some component. If you have critical collapse, this is something which Florian talked about in his lecture on Tuesday, then you have a very specific form for the mass function. It has an exponential cutoff at essentially the horizon mass, upper cutoff, but you get this extended power law so that you extend down to lower masses. Once you have your predicted mass function, the way you get the constraints is you have the constraint F max m, which applies for in the monochromatic case. You then basically have to integrate over the mass function and have to say that the combined integral has got to be less than 1. And then what you do is, having done that, your mass function, remember, is going to depend upon the fraction of the dark matter, but it's also going to depend on parameters which are going to describe the mass function, which are generally twofold. There's normally two parameters, and for example, for the log normal case, it's the central mass, MC, and it's the width of the the distribution. But whatever your model is, there are always two parameters. So this is the input, and then having got the constraint, you're then able to get, having got the observational constraint, which is this one here, you combine that with your information on the mass function to get a constraint on the fraction of black holes as a function of MC and sigma. Remember, FB is the total dark matter fraction. So what you can do is now, and I should say that this is discussed in many papers, but the first paper, which I think is, well, I'm sorry, it's a bit boastful, but I think the best treatment was the paper done with Rydell, Tenkanen, Veskonen, and Vermeij in 2017, where there's a bigger discussion of that. But many other people have looked at this, including Florian. But anyway, the point is that if the constraints you get out of this are shown here. So, for example, if we take the, I'm just taking a subsample of the constraints from the, I think this, well, yes, this is from the Japanese paper. This is the monochromatic case, and these are the various color-coded constraints which we had before. If you got an extended mass function, let's say we've got the log normal case, the first thing to point out is that the constraints themselves change. These are what the constraints are. You see, the naive approach is you take the monochromatic constraint and then you just put an extended mass function. But that's wrong. That's what people used to do. You can't do that. You have to, the constraints themselves change. And of course, they change in a way which depends upon the value of sigma, but it's a constraint on FB as a function of MC. So this is the constraint on the total dark matter density for a given value of MC, where it peaks, and for a given value of sigma. You get different constraints for different values of MC and sigma. So that's how it works. It's more complicated, but this is probably the more realistic situation. And then when you've done that, you can get constraints on sigma as a function of m. So you're constraining, let's see if I can move this out of the way. You can then constrain those. That's how you get the constraint on the parameters. Remember, you're trying to ask, can f be 1? And if so, in this diagram here, f equals 1 corresponds to the dotted line. You know, that line there dotted, I think, corresponds to f equals 1, for example. So you can see the way the range for this log normal case. You can see the mass range in which the black holes can do it. But again, you have to do it for each case. So it's a complicated problem, but that's what you have to do. Actually, I should have put this slide first, but qualitatively the point is this, that most constraints assume a monochromatic mass function. So can we evade, the question you want to ask is, can we evade the standard limits by having an extended mass function? And this is a two-edged sword. This is what Florian and myself and Sandstad pointed out. And the reason it's a two-edged sword is that obviously in some sense you may, if you've got an extended mass function, it's possible the primordial black holes can provide the dark matter when you integrate over mass, even though it's only a small fraction of mass of the dark matter in any particular mass range. So that's good. But the other side of the sword, the bad news is that even if you avoid the constraint on one mass scale, it's possible that you may violate the limits at some other mass scale with an extended mass function, and so that's more controversial. And so that slide really should have gone before this slide. I've got them in the wrong order, but this is the detailed analysis where you can see precisely. This is why you have to do the calculation much more carefully. Now, finally, I want to say something about the LIGO again, because LIGO, the LIGO Virgo Kagros, I should say, I showed this diagram in my first lecture. And of course, you remember the question was, these are all the LIGO masses. I think there's something like 50 now, and they're shown in blue. And remember, the point was they're more massive the primordial, the normal black holes, which we know exist from binary, X-ray binaries and things like that. And so that raises the possibility that they were primordial black holes. I mentioned that. But I want to say, actually, there's now more evidence for this. And this comes from the LIGO website. These are all the events. These are all the LIGO events which have now been detected. And you can see that each little square corresponds to an event, and the two little black dots correspond to the original black holes, and the big black circle represents the merged product. Well, you can't take all that in, but I want to show you the following. The key thing about stellar black holes is that they don't explain all the mass ranges. There are certain mass windows. For example, these black holes in red, which seem to be in the mass range in which you shouldn't have black hole remnants, because you've got the pair instability. This is basically between 60 and 140 solar masses. There should not be stellar black hole remnants in that mass range, because those black hole, the precursor stars, explode through the oxygen instability, the electron pair instability. And yet, here are the objects which are in this mass range. And the squares, the red squares, I guess the ones which are dotted, Florian can correct me, I suppose there's some uncertainty about that. Is that the point, Florian?
Well, I mean, if you look at I think it's, first of all, the little red boxes should be a little bit more towards, I mean, they're a bit off.
Yeah, I can see they're off, yes.
But nevertheless, I mean, I think with these dashed lines, you see the progenitor stars or the progenitor black holes are very close to the lower limit. I mean,
yes.
like 65, for instance, and there has been a debate in the literature whether it's exactly 60 or it's 65.
Exactly.
Or
Thank
so.
you for that.
That's why they are drawn a bit cautiously.
Okay, that's fine. Thank you, Florian. But the point is, you only need one of these things to show there's a problem with the stellar origin. But there's another mass window, and this is the lower mass gap, because between 2 to 5 solar masses, you don't expect to have black holes as stellar remnants either, because that's the mass range in which you get neutron stars rather than black holes and things. And yet again, we've got 3 candidates and possibly a 4th are in this mass range. Now, of course, there may be caveats, maybe there are ways you can get black holes after all, but the most natural scenario is not stellar. So this is why we're excited that at least some of these objects may be primordial black holes rather than stellar black holes. And as I mentioned yesterday, this is it's probably not the mainstream view among the LIGO people, but it's probably the mainstream view among the PBH enthusiasts. And the other thing is, there's the asymmetric. The point is, you can measure the mass range of the progenitors, and you expect this to be, pretty close to 1 with stellar black holes, but it can be less than that for primordial black holes. And these are the subset which have got the mass ratio less than 0.25. So again, these might be primordial black holes. I forget whether these are the same ones in the mass gap, Florian, or not, but they're probably. Let's just have a quick look.
Yeah,
there's probably some. There's probably. Oh yeah, there is a. Oddly enough, I not thought of it. There. Well, I don't know, but anyway, this is all really exciting. That perhaps there is already positive evidence for primordial black holes. These are some of the papers which have. This is hot off the press, so to speak, and you can see here that they're claiming that there's we report observation. The combination of the mass ratio, the component masses, and the inferred merger rate for this event challenges all current models of the formation and mass distribution of compact objects. And this is the mainstream LIGO paper. Okay, so I think this is remarkably significant. And then there's another paper here where this is a paper by Foucault et al., where these have got events where they've got possible subsolar events. Now remember that the key signature of primordial black holes is going to be a subsolar mass, because you don't get stars smaller than the solar mass. leaving black holes smaller than the solar mass. And so there are 4 subsolar candidates. And so you can probably detect both myself and even Florian, you can see from the look on his face, is excited by this. However, I don't want to oversell this, but this is the smoking gun. Now, so I hope I've whetted your appetite. So most of this lecture, I've been talking about constraints. And you might think that's a bit dull, but I've ended it by arguing that actually there is positive evidence that the dark matter could be primordial black hole. But it's not just dark matter, and this is what Florian is going to go on to describe. This is describing our recent work with our collaborators, Juan Garcia Bellido and Sebastian Kless and Michael Hawkins as well. So I'm going to now, I don't know, did we want a break? We didn't have a break yesterday, did we?
Yeah, so I think it's also we started late, so maybe it is fine to go straight away. I mean,
Okay,
no.
well, certainly if we want to keep within the 2 hours, at the moment, Florian has an hour, so we're going to be, well, we started 15 minutes late, so this is fine. So Florian, no break, I'm afraid. You're probably exhausted by listening to me, but I'm afraid you have to go straight on and regard the audience.
So what you said is so exciting and so inspiring that I'm anything but tired, and I'm thrilled to talk about this the model, which I think is just bringing so many things nicely together. So let me share my screen.
You now take over.
Yeah, so let me just do PowerPoint and share, and then I press this one probably. Can you see my screen?
Yeah.
Hello?
Yes.
Yeah, okay. Very good, excellent. So I think in the last lecture, we pointed out although some ingredients which will now come together in order to constitute what we think is the most natural scenario to produce primordial black holes, not only as dark matter candidates, but also as solutions to actually numerous cosmic conundra. But before jumping straight to the meat, let's say we need to take a step back. And what's this? Yeah. So let us look onto the history, or the thermal history more precisely, of the universe. Now, this is a diagram showing the relativistic degrees of freedom, so the number of relativistic degrees of freedom as a function of temperature. Here is a mega electron volt unit, and the timeline goes from right to left. So universe is hot in the past, and then it cools down. And when it cools down, successively more and more particles become non-relativistic. And so that means the number of relativistic particles decreases. I mean, first, of course, we have the heaviest particle first. So we have the top quark, then there's W and Z boson, there's the proton, then there's pions, and then there's electrons. So successively, the number of relativistic degrees of freedom decreases when the time progresses till today. Now, this is interesting by itself, but it has more consequence. It has a lot of consequences, and one consequence is that it changes the equation of state parameter W, so the ratio of the pressure to the energy density. You can see here it's when it's the same time or same temperature scale on this axis, and always when you have a drastic change in the relativistic degrees of freedom, you would have a dip in this equation of state parameter W. Now, of course, the strongest one is around the QCD phase transition, which is around here. And you have the pion plateau, you have E plus and minus annihilation. So you have different events that lead to a dip in the equation of state parameter. But if you remember from I think one of the early parts of the first lecture is that the equation of state parameter basically controls the threshold in overdensity above which primordial black holes form. I mean, it's sort of understandable if you are in a radiation-dominated environment, which we are basically in, and then you have a large overdensity, say, of inflationary origin, and that wants to collapse once it's allowed to causally by re-entering the horizon at a certain scale. And then the pressure sort of works against it. If you lower the pressure, so if you lower the equation of state parameter here, you would make it easier. And now you don't only make it a bit easier, you make it a lot easier because there's an exponential dependence on this equation of state parameter. And that actually leads to, if you have mass function, if you sort of come in with a spectrum of large overdensities, and I will tell you details about this because it's a bit overwhelming when you see it for the first time. That will lead to very particular peaks in the primordial black hole mass function. Now, so here you see the dark matter fraction in primordial black holes on this axis, and on this axis you see the primordial black hole mass in units of solar mass. Now, the mass function has been assumed, the initial mass function that then gets massaged, say, by the thermal history of the universe, by all these different events like the QCD phase transition. The original mass function is put in, is just basically an almost scale invariant mass function. It has a little bit of a spectral index, and remarkably, the spectral index is this NS. You can see here, we checked for different values. And what is really remarkable, so if you have a larger amplitude and the whole integrated amount of primordial black holes is really 100% of dark matter, if so, then you basically are determined with your choice of the spectral index. I mean, when you choose the spectral index to large, you overproduce light primordial black holes. This is the green line, and you if you have it too small, you overproduce primordial black holes, which are on the heavy side. Now, and this is really, look, in the third digit, we have a change. It's really narrowly determined. But what is really remarkable, that the thermal history of the universe tells you several things, and also it tells you the location of the peaks, but not only the location, but also the relative height, which can explain, I mean, numerous conundra. There are more slides to come, so don't worry. All these bumps will be related to specific observations later on. But let me here again relate this to these different events which you have. So when different particles become non-relativistic, so the electroweak sector you have probably here, QCD events start kicking in here. And then you have E plus E minus annihilation. And you already see here that this E plus E minus annihilation is around the mass range which you associate with supermassive black holes. This mass range is around planetary mass, and this is around solar mass, and here a few tenths solar mass. So this is really in the LIGO range. And again, the positions of these peaks and the relative amplitude is all given by the thermal history. So it's not an input, it's not small parameters which we tune. We basically have just two input parameters. It's the amplitude and it's the spectral index. But the spectral index is basically the same as measured by Planck. So let me go through these individual bumps now and try to show you and demonstrate to you that these could explain certain previously unexplained findings. Now, let's go. Let's start with the first leftmost bump, the planetary mass bump. So there was a microlensing survey made by Ogle, or the Ogle microlensing survey, and they detected a number of populations. They're a long time scale population, which is not shown here, but which is completely understood. And when I say a time scale for microlensing, I mean, microlensing, let me just briefly explain, you don't resolve as individual images like in strong gravitation lensing. You just have a magnification of a light curve. So you have a source at some point, you have and the lens passing between you and the source, and you get a magnification of the light curve. And depending on how long this lasts, we talk about micro lensing timescales. So, and the population which was not really understood is has a time scale of about a few hours. And of course, people try at first to understand this by looking at sort of standard explanations. And the standard explanation would be, we use free floating planets. But it turns out, I mean, here in this diagram, you basically see these short, observed 6 events with this short time scale. And here's a big or a beginning or a part of them long time scale events, which basically main sequence stars, neutron stars, brown dwarfs, and so forth. But these ones are the ones I'm talking about, the short time scale ones. And the point is, if you want to explain it by free floating planets, you better have a whole lot of them, actually so many that it's unfeasible. So you would need about 1 or 2% of all the dark matter being free floating planets, which is, I think most people would agree that it's unfeasibly much, and you would not be able to explain this in a physical, meaningful way by this type of explanation. And the authors were not really coming from the primordial black hole side, but they were nevertheless looking for explanations, because they found these short timescale events, which are definitely there. And they said, well, this is actually consistent, and our best guess would be that these are planetary mass primordial black holes, which is sort of shown in here, where you have the primordial black hole dark matter fraction versus mass. So it's in a planetary mass range, and it's a few percent. And the other region here, which is shaded, this is an excluded region by another microlensing survey. But you can see you don't touch really this when you could probably touch, but you don't need to go into this region. You can be outside. You're not sort of threatened by another constrained region. This is one part. Then there is quasar microlensing. So if you look at microlensing of quasars, and typically people try to explain this by stars. So you have the stars as a lens. Probably with a number of them, you can entertain this possibility, but not for really a number of them. I mean, there's a number of them, probably 24, that are sort of misaligned so much that it has been calculated that the probability that the lensing occurs due to stars is 10 to minus 4. That's by our esteemed collaborator, Michael Hawkins. And so this also shows that there is another lens needed. I mean, of course, you can come up with other explanations if you like, but sort of the best guess would also be primordial black holes. And that's in fact what he writes. It's argued that the most plausible candidate for the microlenses are primordial black holes. This is another sort of, and here you see the mass range. So it's somewhat below a solar mass, and primordial black holes could equally, could really well explain this. And also this is just at the sort of rise. If you come from the lower mass, it's a rise of this peak. So that can very well be explained by our mass function, for instance. Now, if you come back to Ogle didn't detect only the short microlensing events, or the short timescale microlensing events, but also some longer duration events. Now, some of which have Gaia parallax measurements that suggest that these are really dark lenses. And now for black holes, it's fine, but the problem is that there is a population, and I don't know, around 20, I guess, which is in the lower mass gap. I think Bernard mentioned this before. There's a mass gap which lies roughly between 2 and 5 solar masses. So it's too heavy for neutron stars, and it's too light for black holes. So, or for, say, stellar mass, stellar origin black holes. But primordial black holes don't have this restriction that astrophysical black holes have. They could really explain this. And actually, if you look at this diagram, we're talking about those that are really close to the peak of our distribution. So that's also something what our model or our scenario could supply. There's another interesting observation, I think, first done by Kaszlinski, talking about a spatial correlation, source subtracted cosmic infrared and X-ray backgrounds, and these could be explained also by primordial black holes, namely by through Parser fluctuation in the number density, which would grow all the way from radiation equality up to today. And you get some structures where you have star formation, and these stars would emit in the infrared, while the primordial black holes through accretion would emit in the X-ray. So therefore, having some generating some spatial correlation, and this is also what is sort of at the heart of our predicted mass function. Then there's another interesting observation regarding ultra-faint dwarf galaxies, namely that none are observed below 10 to 20 parsec. And this could be due to a dynamical instability originated from the presence of primordial black hole dark matter. And there's been, by Baldrini et al. And others, there have been really numerical simulation. And actually, it looks like a few percent of the dark matter around, say, 25 or a bit more solar masses could really explain the lack of ultra-faint dwarf galaxies of below a certain radius. Now, Bernard already mentioned Ligo Virgo, and that slide is a little bit outdated, but it's nevertheless valuable to show because it shows actually the prediction that we made. So the first version of our paper, I must bring it into your focus, has been put out before the LIGO 03 events were reported on. So this is here, you see, this is the two individual merging black hole masses are on these axes here. It's in units of solar mass. And we predict actually from our mass function, you can see that basically you have sort of a big peak around the solar mass, and then there's another peak around 10-ish solar mass, and of course the detector sensitivity is such that you would have much higher sensitivity here around 10-ish solar masses, but nevertheless, since the peak is so strong here, you would get also peak around here, but also low mass ratio mergers, and Bernard mentions in one slide, and this is actually what the LIGO collaboration found really challenging to explain with any of the standard scenarios. And actually here in this lower panel, which is the same, basically showing the same detection likelihood, and you see when the first three events, because from the 03 run of LIGO, 3 events came out first, and these 3 events basically, let me see here, they were exactly at these predicted likelihoods where we predict a large probability for these mergers to happen. Of course, now you have many more, and they populate nicely this diagram, and so it's interesting to see how one what one learns also for fundamental physics, because bear in mind that actually primordial black holes, and we mentioned this before, are a unique probe at the physics at a small scale. So it's conceivable that in the future, by having, say, 10,000 of observations, and we will go to that level, we could constrain the physics at the cosmic microwave background, because it's still, sorry, at the I used the wrong word, at the QCD phase transition, constrained physics at the QCD phase transition, and there's still uncertainties. I mean, for instance, we don't know the level of lepton flavor symmetries and so forth, and this could make a difference, but this could be really also try to narrow it down by observations from the gravitational wave astronomy. So that's a fascinating prospect to sort of not only use primordial black hole observation or the observation of black holes to constrain primordial black hole scenarios, but also to really constrain the physics at these early times, which are not really accessible by that means. Now, one thing I like to draw your attention to is that in the scenario, and in most scenarios, in the time we talked about, which is collapse of inflationary density fluctuations during the radiation dominated era, then you would end up with basically a spin distribution centered around 0. And actually look at this. So here's the effective spin parameter. So the effective spin parameter basically is a weighted projection of the individual spins of the black holes onto the angular momentum of the whole system. Of course, the projection to be 0 can mean if you just have anti-aligned spins, right? But of course, there's no reason that all spins should be anti-aligned. So if you observe a huge ensemble, and now we are approaching this, and these are a number of LIGO events, you see, I mean, of course, the individual error bars are large, but you see that they're all consistent. Yeah, they're basically all consistent with 0, and some are a bit higher. But I mean, you have a distribution, so it's expected to have some outliers. And also, another important aspect is that, I mean, of course, we are advocating a primordial black hole explanation for a lot of mergers, but it's not excluded that you have stellar black holes. And in fact, an interesting research focus now is to look to disentangle these populations, because you can have stellar origin and you can have primordial origin. But from the primordial origin, which we expect to be the dominant population, you should expect very, very little spin. And that's very consistent with the data. Another thing is that, coming to the last bump, is that our mass function also predicts the right amount of supermassive black holes or seed for those. You need, I mean, this calculation admittedly can be a little bit refined, so you would get some accretion around here, sort of bringing this curve here, which shows this is the black hole mass, and that's the sort of the halo mass. And you could sort of bring this curve, our predicted curve, a little bit up by accretion. So this should in the next iteration include more refined accretion physics, but this is already showing you that you get sort of a nice explanation by this mass function. I told you, and this is probably briefly, so let's see how much time. Yeah, I have time. So the mass function, which I showed you, had 2 parameters, and like an amplitude and a spectral index. So the spectral index was assumed to be constant. But also what we know from Planck say that, at least at these scales where Planck measured, which are very different, remember, but nevertheless, the spectral index had a running, or has been shown to run. And if you include this running, you actually get a better agreement. So it can be an improved, I mean, the scenario can be improved to be more consistent, actually even more consistent with the galactic center supermassive intermediate mass black holes, and also with some accretion limits by introducing a spectral running. I think it's a similar spectral running which you observe in Planck. But of course, that is currently under research, but that probably shows you a direction in which refinement of the scenario could go. And also another thing, it's a recent paper by Horace Garcia-Bellido and Ceres, who made a really large n-body simulation. It's large in terms of particles and large in terms of time. So it took the age of the universe. And what they found actually is that you don't have a cusp and you don't have a core. What you do have when you have primordial black holes in the constituting the dark matter halo, then in the galaxy, you would it's sort of a ring-like structure, and then it decays. So you get the same rotation curves, you get the same sort of profile at larger scales, but it's a center. Basically, you get a more or less empty region, and that comes from black holes being scattered among themselves and with the central black hole. So you get an empty region, and you get a hill, and it sort of transitions to sort of the known and established dark matter profiles. But there are more. I mean, so far there's no good explanation for these fast radio bursts, and primordial black holes could conceivably account for this by you know, when you have, say, neutron stars, or you have pulsars that are sort of interacting with primordial black holes, you could trigger some emission. In a very similar way, the so-called missing pulsar problem can be accounted for. So the missing pulsar problem tells you that, contrary to your expectations that you should see a certain amount of pulsars towards the galactic center also, not only, but also, you don't see in the innermost, I don't know, 10 or so parsec, you don't see any of these, even though you should. And a bit further, that's probably an order of magnitude or so further distance, you do not observe old pulsars. And this could also be explained by primordial black holes, who sort of merge with or interact with them and sort of eat them up from the inside. So they sink to the centers, and they would just consume their material. And so they sort of clear the innermost part of the galaxy from these objects, particularly old ones. And you know, if you have primordial black holes being the dark matter, you of course have higher concentration of primordial black holes towards the galactic center. They can all, I don't want to go too much into this because there's more material that I like to convey, but briefly mention that certain non-flat rotation curves at high redshifts can also be explained by primordial black holes. So can high velocity stars, by which actually would be emitted by sort of slingshot mechanism from primordial black hole binary system or intermediate mass primordial black holes. It could also explain the Hubble tension, if it exists, because there's some debate. I put it in gray. Some people attribute this to a calibration issue, for instance, so I don't want to go too much into this. And there are actually more of these points, and to all of these you can explain in a lot more detail why primordial black holes are a good solution. But I hope to have conveyed that there are a number of conundra in our beautiful universe, to which primordial black holes in general, in particular those originating from our mechanism, from the thermal history of the universe. It's not really ours. It belongs to the universe in some sense, because it's really beautifully said by thermal history that this mass function could account for all of the things which I just presented, and there are actually more. Now, let's have a little bit a break in terms of the narrative, or since, I mean, before I was advocating that primordial black holes could be all the dark matter and explain all of these nice these puzzles that we find in the cosmos that I mentioned. So, but of course, as like Bernard said, primordial black holes are also interesting, very interesting, even if they are only a fraction of the dark matter. And always when you talk about a dark matter fraction in primordial black holes, so FPBH less than 1, apparently there must be something else, right? That's the logical possibility. And then the question is what to assume, what could conceivably assumed, what could be there. And one thing is that could be there that are particles, say dark matter particles, and these particles could be WIMPs, they could be stereoneutrinos, they could be axion-like particles, all sorts of particles that constitute the dark matter together with primordial black holes. Now, what would happen? So since primordial black holes are around for a very long time, already in the radiation-dominated era, they would accrete, or they would capture these particles, and a halo would build up. And that's it's basically a universal feature what happens. So basically, whatever particles you put in, you would get a halo in some form. Now, when you use this, and if you focus on WIMPs, because it's probably the most standard and most well discussed dark matter particle, then if you take WIMPs, then WIMPs, at least most studied WIMPs, they are studied also by annihilation, or by the annihilation characteristics. Now, when you look at annihilation of WIMPs, it's important to know that the annihilation rate goes like the square of the number density. And I told you about this halo formation. Of course, a halo constitutes a large overdensity, and if you wish, a density spike. And of course, this density spike will massively enhance the annihilation rate of the WIMPs. And that's one, how we proceed. So we first calculate, or not only we, that's work dating back to Eroshenko, and probably even earlier works, and there's work by Bushena, and there was Luca Visinelli and myself, Tommy Olsen, involved, work by Adamek and Burns, and also later work by Bernard Carr, Luca Visinelli, and myself. So one first calculates sort of the density profile of the WIMPs that are captured. Then one can derive from this annihilation rate and compare the signatures to the galactic or extragalactic gamma ray backgrounds. And that's basically in the first step. The results for the first step are shown in here. So here we have the density of WIMPs in gram per cubic centimeters. It's a function of radius. And it's basically both plots are basically the same, but for other primordial black hole masses. So here we have 10 to minus 12 grams solar masses. Here we have 10 to minus 6 solar masses, a solar mass, and 10 to the 6 solar mass. So a rather wide mass range. Actually, we studied an even bigger mass range. And the different colors are for different masses of the WIMPs. We assume the standard cross section of this 10 to the 20, I think 10 to 26 gram per cubic centimeters is the standard annihilation cross section. And so you see here, indicated by the solid line, that the halo, which we calculate, we derived, which formed initially. But then, of course, over the time, you have self-annihilation. You have annihilation of the dark matter particles to themselves, because the density is very high, and over the course of time, you find that the center part of the halo plateaus out. So actually, you find different plateau in the present day halo. So assuming they exist. So then you find a plateau in the middle, and that then falls off at a certain distance. And actually, we found 3 different types of fall-offs, so depending on the mass range. Sometimes it's visible, sometimes not. The outermost is always this R to minus 9/4. Then there's an intermediate range of R to minus 3/2, and then there's even innermost region, which is mostly sort of annihilated away. But initially, it's there. In some cases, you have this R to minus 3/4. So one can precisely calculate the spike, and with this knowledge, you can calculate the annihilation compared it to it's here the extragalactic background. The galactic is also what we compared it to, but the constraints are weaker. So in order to have a more clear picture, I focus here and with this plot on the extragalactic constraints. And here you have the primordial black hole dark matter fraction as a function of mass over actually a rather large mass range from 10 to minus 18 solar masses, 10 to the 15 solar masses, so reaching this slab range, a stupendously large mass range for different WIMP masses from say 10 GeV to TeV. So it's going. So it's the TeV is the uppermost line, and you see 2 regions. One is sort of a sloping region and a plateauing region. This depends on how important the kinetic energy of the WIMPs is, and it depends on the size of the black hole, whether it's potentially potential energy dominated, or it's kinetic energy dominated. So, and what you see, these constraints are really strong. I mean, and for especially for solar mass black holes, which are here, you see that even for a TeV WIMP, you're at what, at 10 to minus 9 dark matter fraction, right? And this is so strong that I made it in red with a red box, because it's something which one should keep in mind. If LIGO detected just one primordial black hole, and then of course it means that it implies that you have dark matter, like a primordial black hole dark matter density, which is of course above this one, because LIGO didn't detect so many now. But if just one of these black holes would be primordial, which probably means you have, I don't know, per mil or so of the PBH dark matter density, this would rule out any standard WIMP scenario. That's something which one should keep in mind, that the constraints are really very strong, and actually it's mutually exclusive. So here is sort of a more general plot where we went through a continuum of the WIMP masses, M chi in GeV, and here's your primordial black hole masses, and here you have allowed WIMP dark matter fraction, where the PBH dark matter fraction is just complementary to 1. And what is remarkable here is that for all primordial black hole masses above 10 to minus 8 solar masses and all WIMPs above 100 GeV, actually, both the WIMP and the PBH dark matter fractions are less than 10%. So that means once you have PBHs and WIMPs, in many cases, you need something else. And that's why our paper has also something else even in the title, because that may even hint to a third dark matter candidate. Of course, that requires that you have PBHs and WIMPs, but once you do, when some people believe this, you're in many circumstances led to even consider a third candidate. So, and I think I'm done with my part. I hope I didn't take too long, and I now can hand over to Bernard for sort of important final points regarding this lecture.
Thank you, Florian. Florian, could you unshare, and then I'll share my screen again?
Yes, I just did.
Wonderful, thank you. And so I think we don't need a break, so we'll carry on. We've nearly finished now, in fact. So, great. So let me just now get to this point. So are you now seeing my screen?
Yes.
Great. So I just want to make some final points. One point I want to mention is the fine-tuning problem. You remember that I pointed out in my first lecture that the fraction of the universe which collapsed is necessarily very small, even if you want to explain the dark matter. And so one of the criticisms, and indeed it's expected to be small in most scenarios, but one of the criticisms of the PBH scenario is that it does require fine-tuning. For example, if the black holes form from inhomogeneities, if the homogeneity is a little bit too large because of that exponential dependence, beta exponentially depends on epsilon, then you make far too many black holes. So there'll be all the universe will be black holes. There wouldn't be enough ordinary baryonic material left over to make galaxies. On the other hand, if beta was a little bit too small, if epsilon was a little bit too small, then beta would be tiny and there would be no black holes at all. So a common criticism is, well, why should the collapse fraction be so finely tuned? And let's be a little bit more precise. If, for example, the mass of the black hole making up the dark matter is m, well, if the black hole forms at a time t, we know it's got a mass which depends upon t, and the collapse fraction depends upon m according to this formula here. Beta is fm, and we want fm to be 1, but it scales as m to the half. And so, in other words, if m is very small, then this beta is very small. And in particular, you notice that if the black holes form at the quark-hadron phase transition, which is at 10 to the minus 5 seconds, m is naturally 1, but you see m is basically a billionth, 10 to the minus 9. So the question is, why should the collapse fraction be 1 in a billion? And actually, it's not only beta which is fine-tuned, there's something else which is fine-tuned, and this isn't often focused on. We can take the ratio of the PBH density to the baryonic density, which I'm calling chi. Well, that is just rho PBH is F times the rho dark matter density. And we know what the dark matter density and the baryonic density is from nuclear synthesis calculations. And this is more precisely, it's 6 times F. So this parameter chi, which is the ratio of the PBH density to the baryonic density, is also of order 1. And that is also a puzzle. Why should the primordial black hole density be so close to baryonic density? And indeed, that's whatever your dark matter candidate is, you should be asking this question: why is the baryonic density so similar to the dark matter density? Now, there are actually arguments for why this might be required. If chi was much larger than 1, that is to say, if the fraction of primordial black holes was far larger, if the ratio of the black hole density to the baryonic density was far larger, then what would happen is what is called T-equilibrium. This is the time at which the matter and radiation dominate universe. The matter and the radiation densities are comparable at the time T-ec, which is about 10 to the 4th years in the standard picture. Decoupling is the time when the matter decouples from the radiation. That's about about a million years. Well, actually, it's about 100,000 years more precisely. Now, in the standard picture of cosmology, Big Bang cosmology, those times are roughly comparable. I mean, T-ec, as I said, it's about 10 to the 4th years, and T decoupling is 10 to the 5th years. And they happen to be pretty close. And again, that's sort of a coincidence within the standard picture. But the point is that if chi was much bigger than 1, T-ec would be much, much less than T decoupling. But what that would mean, because as you know, the T-ec is determined by when the matter dominates the radiation, and that happens earlier if you've got a lot of matter. Matter here is including the dark matter. Now, but what would that mean? That would mean that actually most of the universe will be in black holes, and there wouldn't be enough baryons left over to make galaxies. And that wouldn't be very good news because we wouldn't be here. On the other hand, if chi was much less than 1, in other words, if there weren't many primordial black holes, in this case, T-ec, oh sorry, there's a typo, that's not T-dec, that should be T-ec, will be much bigger than T decoupling, because then you'd have to wait later. In fact, it would be the baryons which would be determining the time of T-ec. But in that case, the fluctuations will be too small to make galaxies, by which I mean that the microwave background tells you what the fluctuations actually were. But those fluctuations, they're about 10 to the minus 5. That wouldn't be enough to make galaxies unless you have dark matter. If you have dark matter, what happens is the dark matter potential wells are larger than the baryonic fluctuations tend to get wiped out, but the dark matter potential wells remain, and that allows the baryons to fall inside after decoupling. So in some sense, it's well known that you need dark matter in order to get galaxies forming. The existence of the microwave background fluctuations requires dark matter in order to allow galaxies to form. So what I'm saying is that there are good arguments why chi has to be quite close to 1. And these might be regarded as anthropic arguments, in the sense that if chi wasn't close to 1, we wouldn't be here, because there wouldn't be galaxies, either because there weren't enough baryons to make galaxies, or the fluctuations will be too small to make galaxies. Now, the A word is unpopular in certain quarters. People don't like the anthropic argument. Many physicists don't like it. They think it's too philosophical or even theological. I have to say, I was one of the people who was a strong advocate of the anthropic principle. I wrote a paper in 1979, which got published in Nature, with Martin Rees, and that was one of the first papers to put together all the anthropic arguments in one place. So, but we got a lot of flack at the time. A lot of people didn't like the anthropic argument, and I remember one of my physicist friends said it was obscene, because it seemed against the concept of proper science. And I think the reason was a lot of people thought that this the anthropic selection implies fine-tuning, and that maybe it implies the existence of God or something to fine-tune, and most physicists don't like God. So, however, nowadays we think a more plausible explanation of the anthropic selection is the multiverse scenario, where you have different universes with different constants, and that we just happen to be in one of the universes which has got the right values of the constants for life, and chi would just then be one more of these anthropic constants. The fraction of the universe collapsing, in other words, might be constrained anthropically. And nowadays the point is, whereas 40 years ago the anthropic principle was rather a heretical idea, it's now almost mainstream. I mean, it's still controversial, but a lot of great physicists like Martin Rees and Steven Weinberg and Wilczek and Susskind and people, Susskind, take this very seriously. Anyway, at the QCD epoch, we've already seen, and Florian talked about this, the mass of the black holes forming is naturally the Chandrasekhar mass. The Chandrasekhar mass, it's 1.4 solar masses. This is the mass required it's an upper limit for the mass of a white dwarf. And in fact, most stars have a mass around the Chandrasekhar mass. I mean, obviously it's not exactly 1.4, but most stars go between something like 1/10 of that and 50 times that. And there are well understood astrophysical reasons for that. So MC is the mass in which most stars exist, but it's also the mass at which the black holes are forming at the QCD epoch. So a rather nice feature of this scenario, which is the one that Florian was advocating in his lecture, is that the dark matter and the visible stars naturally have the same mass, which is rather weird. But the other thing is that the collapse fraction, this collapse fraction here, you can see it's 10 to the minus 9. But it's not only 10 to the minus 9. If you think about it, the ratio of the number density of baryons to the number density of background photons in the CMB is also, it's called eta, and that's also about 10 to the minus 9. Now, that's not a coincidence, it's inevitable, because if you think about what the QCD epoch is, the QCD epoch is when the temperature is of order a hadron mass, which is about 10 to the 12 degrees. And so it's inevitable, if F is 1, that at that epoch, the ratio of the black hole density, or the matter density to the photon density, is just going to be the ratio of the number density of the baryons to the photons, because the photons then have the temperature, the energy of a hadron, of a baryon. It's a proton is a GeV, but the QCD temperature is more like 300 MeV. And so this collapse fraction is simply this well-known cosmological parameter, which is normally called eta. And eta in turn relates to the baryon asymmetry of the universe. You remember the picture is that before the QCD epoch, you have a slight asymmetry in the number of baryons and antibaryons. You have an asymmetry of eta, 1 in 10 to the minus 9. And then when the antibaryons, the antiprotons annihilate after the QCD epoch, you naturally generate a photon to baryon ratio, which is the inverse of eta, which is 10 to the 9th. So there's nothing anthropic about that. It's inevitable that if the black hole forms at the QCD epoch, then this ratio is 10 to the minus 9, which I don't think had been appreciated before. This is all discussed in this paper with Garcia, Bolido, and Kless in 2019. Now, here I've just mentioned the fact that all stars have a mass in the range 0.1 to 10 solar masses. Alpha G is the gravitational fine structure constant, which is about 10 to the minus 40. But what this implies, first of all, is two things. First of all, I mean, you might ask, why should the collapse fraction be eta? But then this suggests, well, maybe the PBHs actually generate the baryon asymmetry. But the other thing is, I'm going to talk about I'm going to talk a scenario. I'm now going to describe a scenario where that happens. But also, this scenario is going to explain why the dark matter and the visible baryons have a similar mass. So let me go on now to explain this scenario. The point is this, and again, this is the same paper as I referred to. Oh no, it's a different paper. Sorry, this is a shorter paper. Actually, and in this paper, Juan is the first author. So this previous paper, there were three of us, but this second paper, Juan was the first author. So in fact, there are two papers there. So should get that right. But anyway, the important point is this: so far, when Florian was describing the formation of primordial black holes by gravitational collapse, we were only focusing on the region which collapsed. But actually, what happens is when a region collapses, it generates a lot of energy, and that energy can be imparted to the outer material and produce an expanding shock wave. And in fact, this is just what happens in a supernova. You know, when a star collapses, it collapses to a neutron star, but then you produce neutrinos which transfer the energy to the outer shell, which expands. The same thing happens in primordial black holes. And actually, I don't think anyone pointed this out till a few years ago. So we point out in this paper that whenever you form a black hole, although we normally focus on the collapsing region, there will be an expanding shell of matter, which gets its energy from the gravitational input of the collapsing material. But this shock is really hot. And this has really interesting implications. So you can think of this, if you like, it's like a supernova, but it's a supernova occurring in the early universe. Well, first of all, it's so hot that you can have C and CP violation of processes occurring, even with the standard model, which is described by what's called the CKM matrix. And then there can be baryon number violation due to phaleron transitions, because that happens when you've got TV collisions, which is what tends to happen. But the other thing is that this process tends to be out of thermal equilibrium, because the PBH collapse does involve a violation of thermal equilibrium. Well, as I'm sure most of you will know, these are the three ingredients for baryosynthesis or baryogenesis, the generation of a baryon asymmetry in the early universe. Now, in the standard cosmology, we know that asymmetry has to be generated, but it's normally assumed that the asymmetry is generated in a very early stage, maybe the gut epoch or something like that, the grand unified epoch. But what we're saying is, well, look, maybe actually the baryon asymmetry, which remember is that parameter eta, is actually generated by the primordial black hole formation. Because you see, the point is that if what you've got to imagine is that a fraction of the universe beta collapses locally in each of those, around each of those black holes, the baryon asymmetry would turn out to be of order 1. Okay, so the amount of matter and antimatter would be about the same. But what then happens is that the antibaryons produced, the baryons and the antibaryons produced in the black hole shock can actually propagate throughout the universe till this asymmetry is basically spread across the whole universe. So what was a local asymmetry of 1 becomes a cosmological asymmetry of beta. So this scenario beautifully explains why the collapse fraction beta is the cosmological baryon to photon ratio eta. I found this such a beautiful idea. I mean, I think we all found it such a beautiful idea. And so we submitted this. Well, no, I won't go into that. Sorry. Now, not only that, this scenario produces a relationship between chi, which is the ratio of the black hole density to the baryon density, and it depends upon gamma. Now, I don't know if I defined gamma earlier on, perhaps, or maybe it was defined in Florian's earlier lecture. Gamma is the size of the primordial black hole to the size of the horizon, the particle horizon. And it's easy to show that chi is just gamma over 1 minus gamma. And remember, this factor needs to be 5. And or was it 6? But anyway, it's 5 here. And this is 5 if gamma is 0.8. So this scenario has a very specific prediction as to what the actual value of chi is, and it simply depends upon gamma, the size of the black hole. So that's giving you something important information about the formation mechanism. And gamma of 0.8 is plausible, but of course it depends on the details of the collapse scenario. So I find this really tremendously exciting. And so, as I say, here was the basic argument. E local, the local asymmetry is 1, but this turns into e to twiddles beta after and chi being 1 after you got the diffusion. And that, you know, there's been some debate about whether the scenario is valid, because it depends upon the fact that the baryons have to diffuse from one black hole to the next black hole. But I won't go into that. All these papers have now been published, although it took us at least a year or so to get through the referees. Anyway, I want to just end this discussion of dark matter. I mean, is the dark matter PBHs or WIMPs? And I think I mentioned in my first lecture, probably most people, to be honest, would prefer it to be WIMPs. And obviously most particle physicists would prefer it to be WIMPs. I don't know of this audience how many people are particle physicists as opposed to cosmologists. I mean, but, you know, basically there are far more particle physicists than there are cosmologists. And also people have, you know, spent their lifetimes thinking about whether the dark matter could be WIMPs, and indeed making experiments to try and prove they're there. So I appreciate that it's not a popular suggestion in certain quarters that the dark matter should be WIMPs. And indeed, sometimes I give lectures to particle physicists. This is in the days of physical lectures, and arguing that actually the dark matter is primordial black holes rather than WIMPs. And I feel rather uncomfortable, because I feel that that cannot be a welcome message for people who spent 50 years thinking about WIMPs. And indeed, I sometimes think I must be the most unpopular person in the room, and I'm even afraid that people will start throwing tomatoes. And well, one of the advantages of a WIMP talk, of a Zoom talk, is I don't need to worry about that. But anyway, I'm sorry if this is an unpopular suggestion in certain quarters, but well, truth is true. Certainly among some of us here, myself and Florian, it's a popular suggestion. But what I want to say is there's an interesting historical analogy between the history of WIMPs and PBHs as dark matter. And it's symbolized in these two diagrams. Here's the famous FM diagram. Sorry, I shouldn't say famous, but I was involved with the Japanese, the paper with the Japanese, where you're basically seeing how F is limited as a function of mass. But the sort of equivalent paper you see among the particle physicists is a plot of the WIMP cross-section against the WIMP mass. So it's a similar mass scale, but this is a WIMP cross-section as opposed to an FM. But you can see the basic idea is the same. As you get more and more data, you get colored regions, and the data is pushing down the limits. So it's exactly analogous. Here we're pushing down the limits, the colored regions. Here you're pushing down the limits. Now, in either case, we still don't have definite evidence. So there is no positive evidence for WIMPs yet. After I know it's a bit depressing, because they've been, you know, you've been looking for these WIMPs for whatever it is, 50 years. But On the other hand, it's not excluded. I mean, it's a bit disappointing not to have found them, but we haven't excluded them by any means, so we might find it with the latest upgrade of the LHC or whatever. And the situation is rather similar. Until at least 5 years ago, all we had constraints and no positive evidence. Now, obviously, you've heard from Florian and myself that there may now be positive evidence for PBHs. So I would say, in my somewhat biased perspective, that if anything, we're swinging towards the PBH scenario now, because there is positive evidence for that. There have been some claims for positive evidence from, for searching, for example, from the underground detectors, but I think that's more controversial. But it's similarly here, all the evidence is controversial. But to me, I see this as a combined effort. We still don't know what the answer is, but it's only the combined efforts of the cosmologists looking for PBHs and the particle physicists that are looking for WIMPs that really seems to be that's the way to proceed, because we just don't know at the moment whether it's me who's wasted 50 years or whether it's the particle physicists who wasted 50 years. We'll have to see. But it's not wasted anyway. I mean, for example, I've emphasized that even if PBHs don't make up the dark matter, they can still do lots of other interesting things. They can be seeds for galaxies and use cosmic rays and things like that. Even if the WIMPs don't make up the dark matter, they do lots of interesting things. There was a time that when people thought neutrinos could be the dark matter. No one thinks that anymore, although the sterile neutrino is a possibility. But we now know neutrinos have a mass, and we know they're tremendously important. So we shouldn't get too hung up about whether things are the dark matter, because really they can be very interesting even if they aren't the dark matter. What's fascinating is something Florian alluded to in his last few slides, that you could have the combination of primordial black holes and WIMPs. But the really interesting result to me is that actually they can't both be important, because of the forming of halos or WIMPs around primordial black holes. Either the primordial black hole density is really low, or the WIMP density is really low, or conceivably both are low, in which case you need a third dark matter candidate. So I'm very pleased that Florian made that point, because I think it's very important. And I should have to say, I mean, obviously we've tried to stress the positive aspects of primordial black holes, and I would just like to highlight that together with Florian and Kless and Garcia Bellido and Mike Hawkins, we're currently writing a review called Observational Evidence for Primordial Black Holes, a positivist perspective. And the point about this, as you may know, the positivists were a group of philosophers in the early 20th century who put a lot of emphasis on you could only believe in things where you actually had positive evidence for them, and all these speculations about things you could never see were not very important. Now, actually, the positivists as a philosophical group rather died out, because there were later developments which showed that that wasn't the case. And indeed, even within physics now, a positive philosophy generally doesn't work, because some people argue that speculations about M theory and the multiverse aren't proper physics because we don't have direct evidence. But I think there is a broadening view of science and physics which says that, well, actually something can be valid and part of respectable physics, even if it's not directly observable. Like you can never see inside a black hole, you can never see quarks and things like that. It doesn't mean it's not physics, because if it's the prediction of a theory of physics, which we believe, then it's part of physics. It's not philosophy, and certainly not theology. So within science, I would say a positive perspective, is still, it's controversial. Some scientists will only believe in things where you can get direct evidence, which is why some people don't like M theory and some people don't like the multiverse. But I think actually quite a lot of physicists now take a broader perspective in which one doesn't say that. However, the point of this paper, I'm really just talking about the word positivist. The point of this paper is to argue that even if you're a positivist perspective physicist, we are now getting positive evidence for primordial black holes. So up to about 5 years ago, all one had was constraints, which was giving you information, which is why we were spending time thinking about these. But now we're getting positive evidence, and that's the message I want to get across. Finally, I just want to talking about the popularity of primordial black holes. I thought it might be interesting to actually show how the popularity has waxed and waned over the years. So let's say it started off with Hawking's work in '71 and then my PhD thesis. And then it was just theoretical speculation. There was a time in '82, I didn't mention this in the talks, Florian didn't mention it, but there was a time when people were interested in primordial black holes forming the Quark Hadron era, which we've been arguing may be the case. But this was by Crawford and Schramm, and they were thinking there would be Jupiter mass black holes when it was a first order phase transition. So that became, by the way, there's no precise definition of popularity here. I mean, it's not, I suppose it's the fraction of physicists who are working on the subject. '93, this is when Hawking started getting the microlensing constraints. Observations, sorry, not constraints. And then the Macho results came in '97, and that produced, as I said, the apparent evidence, that there might be dark matter in halos made of black holes, although it turned out, as I said, to be 20%. So this was the, well, sorry, we haven't got to that stage yet. So this is still the exciting period when it looked as though it could be black holes of half a solar mass. And then there were the predictions that the black holes of that mass that should form at the Quark Hadron phase transition. So the picture's getting better and better. Then, unfortunately, we got all the microlensing constraints, and that said that, well, unfortunately, they can only make up 20% of the dark matter. So that was a bit of a downward. It's like snakes and ladders, the snakes and ladders game. This was a snake. However, then in 2010, people got interested in the possibility that the dark matter could be in Planck-mass relics, something we've actually not really talked about very much, or various other mass ranges. It could be the sublunar range, for example, or it could be the intermediate mass range. So there are a lot of papers, some triggered by observational evidence, but some just from theoretical developments, which got people interested in this subject again in 2010. And then, but then of course, there was a lot of work on the constraints, some of which I discussed in the first lecture this morning, and these came from dynamical and accretion and indeed lensing arguments, and they seem to make it unlikely that the dark matter was primordial black holes, or even existed at all. That was the point of the colored diagram. But then came LIGO, and by now we're in 2015, where we started detecting primordial black holes. And I think that's as far as this diagram goes. I could, I suppose, put another arrow with all some of the more recent work which Florian described in his lecture, but I think this is as far as I've gone in this diagram. But this takes us up to 2020. So this is really the diagram is showing the ups and downs, but the point is right now we're at an up. And I'm really optimistic that but I've worked for PBHs for 50 years, and for most of that time I would have said, well, actually the probability they exist is probably, maybe only 20% or something like that. I mean, obviously there's a lot of interest in with the Hawking results in Hawking radiation, but it all changed. And now, in the last 5 years, in fact, since I've retired, I'm really much more enthused about them. And I would say the probability that they exist, I don't know what to put bet, but I would bet, I think there's at least a 50% chance that they exist. And Florian, I don't know, Florian, whether you want to give a higher percentage than that. I mean, when I say 50%, I'm being conservative. I think
I think I'm more I'm more progressive here. I would probably go even up to 95%. So
that's great. And Florian is younger than me, so the fact that he's saying this is particularly good. And I should say that Juan Garcia Belido, our collaborator, he would give the probability, I think, at 99%. So I think he would, if Juan ever listens to his lecture, I think he would want to say that it was not. He is even more enthusiastic about PBHs than me and Florian, I think it's fair to say. But anyway, and I just have to say, it's been such a pleasure for me to collaborate with people who believe in primordial black holes even more than I do. So thank you, Florian. Anyway, here is my conclusions. Our conclusions, I should say, because I think that Florian will agree with this. PBH studies have already led to profound insights into cosmology and fundamental physics, even if they never formed. I'm here referring, of course, to the Hawking radiation, but the point is that we've argued how you get these amazing constraints on the early universe, which you could only get through thinking about primordial black holes. Now, until recently, most work has focused on constraints, but now they've been invoked for numerous cosmological purposes. And I will just say, dark matter and Ligo, Virgo, these are undoubtedly the purposes which are attracting most attention. Indeed, this is why we focused on them in this lecture, in these 4 lectures. But there are also many other cosmological conundra. For example, seeds of galaxies, and where the supermassive black holes. In fact, I should probably have made that a 4th box. I thought I had made it a 4th box, but the seeds for supermassive black holes in galaxies is another of the really key things. And so that's why we've got this positivistic perspective. Now, and the point is, these are distinct roles. The black holes which make the dark matter and Ligo and make the supermassive black holes in galaxies, they could in principle be distinct populations of primordial black holes, because there are many ways primordial black holes that can form. But personally, I prefer a scenario where the primordial black holes have an extended mass function. And so you're killing all of these problems, killing all of these birds with one stone, so to speak. The stone being primordial black holes. And I especially like the scenario which Florian described in his lecture this morning. It has it's not just an extended mass function, but it's got these bumps, these 4 bumps, which correspond precisely to these phenomena. And as I've argued that the normal complaint that you need fine-tuning, you can get around with the sort of scenario I described just a few moments ago. That PBHs can naturally form at the QCD epoch, and this could explain the dark matter and the baryonic symmetry, and all you need is some sort of anthropic fine-tuning of the collapse fraction. Anyway, that's the end of my lecture and of our lectures, and it's a little bit late. It's past, so we've been 2 hours and 15 minutes, but we're open for questions if you have time. I will stop sharing now.
Thank you for the nice lecture. So it's time for the question and discussion. Any question?
Can I ask a question? I have a question about the Fm function near 10 to the minus 15 solar mass, where 100% dark matter still can be understood by PBH. So you didn't mention much about that reason of the parameter.
Oh, fair enough.
Yeah, and also, please.
Can I share the screen again just to illustrate your point?
Sure.
I've got to find my Florian. Are you happy for me to answer this? You can come in later, of course. Let me just show you I'm going to show you the figure which Florian showed, because this is actually a little bit. Well, no, I can show this. I can show this one here. So here is the diagram which shows the gap. I mean, so even apart from all these caveats like having an extended mass function and things, there was a clear gap here, which is in the mass range you're referring to. So what you're really saying is, well, why are we not focusing more on that? And that's a good point, because lots of people have argued that the dark matter is in this region. And most naturally, this arises if you have inflation, but you have an inflationary scenario which produces a peak in the power spectrum. So there are a lot of papers that produce the dark matter in that range. there are other scenarios which depend on some sort of phase transition involving scalar fields and things like that. Thinking of the paper by Alex Kostenko and his collaborators. So there are scenarios which produce dark matter there. In fact, there are three mass ranges where you can have a lot of dark matter. There's this mass range. There is the mass range in this what we call the slab range, stupendously large black hole, but that can't be the dark matter in galaxies. I mean, it could still be there, but there'll be an intergalactic space. The point we've been arguing is that the dark matter could be also concentrated around one solar mass. But the point, even though that seems to be excluded, and the point I made in my lecture today was that you can get around some of these constraints if the PBHs aren't clustered, are clustered. But now then the question is really, you've got two. If you accept that argument, you've still got two candidates. You've got the asteroidal mass range down here, and you've got the sort of roughly one solar mass region around here. Notice, incidentally, something that Florian pointed out, that the LIGO events themselves, they're coming from something like 30 solar masses. They're coming from a higher peak. The total primordial black hole density, of course, is the entire integration over all these bumps in the spectrum. It's just that the biggest bump is around about a solar mass, which is what Florian introduced. Now, so how do you decide which of these you want? Well, I mean, in principle, either could be correct, and there will be lots of people, especially the Japanese people, have focused on this range. I'm afraid we've not given the references explicitly in the slides, but they are in the paper we've written. Well, we focused on the one solar mass merely because that is what we, myself and Florian, have been particularly excited by. And maybe we should have put a little bit more focus on this other mass window because it's still perfectly plausible. If it turns out that the one solar mass region goes away, then you're going to be forced to this region. And actually, in principle, you could have a spectrum of PBHs in some inflationary scenarios, which has both bumps. I mean, there are people who propose models where you've got most of the mass here in this mass window, but still have enough primordial black holes to make the LIGO events. Remember, the LIGO events themselves probably do not have the dark matter density. I mean, it depends on precisely when the binary is formed, but probably the LIGO events have only something like 1% of the dark matter density. And so, if you can get if you can produce a scenario where the PBHs have two bumps, one in the asteroid or lunar mass range, and another smaller bump at say 30 solar masses, you get LIGO and the dark matter. But we focused on the one solar mass because merely that's the one which myself and Florian are most enthusiastic about at the moment, even though that is the bump which that seems less plausible in terms of this diagram than the lower mass bump. So does that answer your question?
Well, I am also one of the authors who claimed the inflationary models can predict PBH near 10 to the minus 15 solar mass. For instance, particle physics-based inflationary models such as Higgs inflation model can produce a PBH near that region of the parameter space.
Indeed.
So my actual question was about the discovery of PBH near 10 to the minus 15 solar mass black hole. Do you have any idea or?
Yes. Well, I mean, I would say if we go back to the let me just share the screen again. Let me go back to this well, let me show some of the the dynamical limits here and the lensing. I mean, if let's take these two pictures here. First of all, I well understand why you were upset that we didn't mention this. Of course, we haven't mentioned any papers by name. I know about your work, and we should have cited that your work, Parker work, and all that. But we, as you'll appreciate, we haven't cited any papers in the actual slides. I don't know actually whether or what. I'm not sure when your paper came out, so I'm not sure whether we cite your particular.
I will
paper.
send you the paper later.
Thank you, because
Okay.
we should certainly add that. But your question is, what are the ways of detecting? And I would
Right.
say, sharing the screen again, you can see where there were constraints. For example, femtolensing of gamma ray bursts. I don't know if you're in the range which is gets up to Kepler. You're probably to the left of that, aren't you? I think you're probably. So
Yes, I'm at.
although I say the gamma ray burst is now in dotted form because the original arguments didn't seem so good, it's all to do with the size of the region which is being lensed. There are still some, it's possible the constraints are there. So I would say that would be perhaps one of the ways. Improved calculations will be one of the ways of looking for it. And the other way, of course, is the dynamical limits, because in this range, you always had these arguments which to do with the swallowing of the primordial black holes by neutron stars or white dwarfs, or the triggering of supernova. Now, again, these arguments are dotted. The reason they are dotted are a bit technical, because the reason was that the people who were talking about the capture of black holes by neutron stars and white dwarfs, this was going on in the centers of globular clusters and dwarf galaxies, and it depended on what the dark matter density was. And so there were the original papers were assuming something about the dark matter density, in other words, the number density of PBHs for which there wasn't evidence. But that doesn't mean that there aren't going to be improved calculations which would be relevant. And the supernova argument depended upon the fact that if you've got a white dwarf, if the black hole goes through it, it can trigger an explosion. And again, there were technical criticisms of that scenario, which is why it's made a dotted line. But that doesn't mean that those scenarios can't be made more precise and valid. So I would say the best, I don't at the moment know of any positive evidence, but in principle, I think if you did those calculations more carefully, you could actually, as I said before, every constraint is a possible signature. And so notice that the mass range here goes from 10 to the minus 15 to 10 to the minus 9. And in the previous one, it's about 10 to the minus 16 to 10 to the minus 17. So I would say that is probably, that's the best hope. Florian, would you like to come in here? Have I missed out anything?
No, there's really not much to add from my side. I mean, it's really nicely explained. I mean, at the beginning, I think you pointed also the dotted lines out, but also when we go to our, let me just share my screen here. So, well, I mean, we had actually sort of in 2016 a rather different picture. So, I mean, the question or the discussion just arose, why aren't more papers focusing on this range or in general to focus on this mass range? But actually, only a few years ago, it appeared to be closed also, right? So that's also interesting to have a look. It's I think we should always keep in mind that when wondering why a certain mass range has not been explored that much, it can be due to the fact that just 5 years ago, that was completely covered by constraints. And I think you mentioned this also by some dotted lines. And here there were the Newton star constraints, and the Newton star constraints come about by us looking in the sky and seeing Newton stars. And if you had a too high a fraction of primordial black holes, they would just destroy these Newton stars. And but it turned out that for these papers, a too high dark matter density in the globular clusters where they looked for these Newton stars was assumed, and so these bounds basically completely disappeared. And so they're all a function of time.
And so, in fact, can I share the screen again? If
oh yes, please.
I'm going to show one more slide, which is relevant because it depends actually on precisely what mass range you have in mind, Sion-chan, but the this slide I'll remind you of. These were the evaporation limits, and there are more complicated ones. Now, if your mass range is way down low, you know, something like 10 to the 17 grams, which is still the asteroidal mass range, then there are all sorts of other possible signatures, and they're shown in this figure here, you know, where obviously you can then, the point is that these black holes are not completely evaporated. They're still constrained by the you know, the gamma ray background, the galactic gamma ray background, and the various cosmic rays. But in principle, you can see in this range here, remember f equals 1 is the dotted line, so you can see that there are lots of observations around about 10 to the 17 grams where you can start getting positive evidence. But
from Hawking radiation, right?
From Hawking radiation, this is, all of these are associated with Hawking radiation and the emission, but of different types of particles. But Seung-chan, I don't know if we cited your paper because it may have come out after our review. So could you do us a favor? Could you send me an email with the reference to your paper, because then we can make sure we refer to it. But of course, you're quite right. I mean, I'm sorry we didn't emphasize this possibility more in our lectures. It was just a reflection of the limited time. If we had another hour, we would have talked about your paper for an hour, but I'm afraid we run out of time. So let me stop sharing now. Yeah.
Thanks.
I have one question about your comment on the baryogenesis by primary black hole. And in the usual particle physics model for baryogenesis, people say that the Kobayashi-Masaoka phase in the standard model is not really enough for the CP violation needed for baryogenesis, and we need some additional CP phase. So in your scenario with primordial black hole baryogenesis case, do you need some new source of CP violation or not?
Well, the claim is, and again, I'll share the screen again. The claim is, in our scenario, if I can just find the right slide,